Imagine two particles. They're connected somehow. We don't know how. We don't know why. Now separate them. Put one here, on Earth. Send the other to the far edge of the galaxy, billions of light years away. Measure the first particle. At that exact moment, not a second later, not a millisecond later, the second particle reacts. Instantly, faster than light. This shouldn't be possible. Einstein knew it. He spent years trying to prove it was wrong. He called it spooky action at a distance, and he hated everything about it. But here's what Einstein didn't live to fully accept. Every single experiment we've run since then has confirmed it. The connection is real. The instant reaction is real. Two particles, any distance, instant connection, and nobody, not a single physicist on Earth, can fully explain why. My name is Quantumatrixx, and today, we're going to investigate one of the deepest mysteries in all of science. Not just what quantum entanglement is, but what it means for space, for time, and for the nature of reality itself. Let's follow the evidence. To understand why this is so strange, we need to go back to 1935. Albert Einstein, the most famous physicist who ever lived, was deeply uncomfortable with quantum mechanics. Not because he didn't understand it. He understood it perfectly. He was uncomfortable because it seemed to suggest something he found philosophically unacceptable. That reality, at its smallest scale, was fundamentally random, uncertain, unknown, until you looked at it. Einstein believed the universe operated by clear, fixed rules, that if you knew the position and speed of every particle, you could predict everything. God does not play dice, he famously said. Quantum mechanics disagreed entirely. So in 1935, Einstein teamed up with two colleagues, Boris Podolsky and Nathan Rosen, and published what they thought would be the decisive argument against quantum mechanics. It became known as the EPR paradox. Their argument was elegant. If two particles interact and then separate, quantum mechanics says measuring one instantly affects the other, no matter the distance. But that would require information to travel faster than light. And nothing travels faster than light. That was Einstein's own law. Therefore, they concluded quantum mechanics must be incomplete. There must be hidden variables, some deeper layer of reality that explains the connection without breaking the speed of light. For nearly 30 years, nobody could prove them wrong. Then, in 1964, a physicist named John Bell found a way to test it. Bell designed a mathematical inequality, now called Bell's theorem, that would hold true if Einstein was right and be violated if quantum mechanics was right. The experiments began. One by one, decade after decade, Bell's inequality was violated. Quantum mechanics won. Einstein was wrong. The connection between entangled particles is real. It is instantaneous, and it does not care about distance. But here's the mystery that Bell's theorem opened up. It answered one question and immediately raised a deeper one. If the connection is real and it's instantaneous, then how does it work? Let's slow down and really look at what's happening here. When two particles become entangled, they enter what physicists call a superposition, a shared quantum state. They're no longer two separate things. In a very real sense, they're one system. Here's the clearest way to think about it. Imagine you have a pair of gloves. You separate them into two boxes. You ship one box to Mars without looking inside. You open your box, and it's a left glove. You instantly know the box on Mars contains the right glove. No mystery there. The gloves were always different. You just didn't know which was which. Einstein argued entanglement was exactly like this. The particles always had their properties. We just didn't know them. hidden variables, nothing spooky. But here's where quantum entanglement breaks that analogy completely. The particles don't have fixed properties before you measure them. Before measurement, the particle isn't spin up or spin down. It's both. Simultaneously, the act of measurement is what forces it to choose. And at that exact moment, the entangled partner instantly becomes the opposite, no matter where it is. This isn't a metaphor. This is what the mathematics says. This is what every experiment confirms. The particles are not like gloves that were always a pair. They're more like a coin that exists as both heads and tails simultaneously. And the moment you look at it, both coins snap into opposite states at once. Across any distance, instantly, physicists have now performed entanglement experiments across distances of over 1,200 kilometers. Using satellites, the connection held, the instant correlation held. And it gets stranger. In 2022, the Nobel Prize in Physics was awarded to 3 scientists, Alain Aspect, John Clauser, and Anton Zeilinger, specifically for their experimental work on entanglement. The Royal Swedish Academy of Sciences called it proof that there is no going back to a classical view of reality. The Nobel Prize for proving the universe behaves in a way that Einstein refused to accept. So we know entanglement is real. We know the correlation is instantaneous. We know distance doesn't matter. What we don't know, what nobody knows, is the mechanism. How does one particle instantly know what happened to its partner? There are several theories. Some say the particles share information through a layer of reality we haven't discovered yet, a deeper quantum field, invisible to our instruments. Others argue that entanglement proves the universe is fundamentally non-local, that the concept of separate locations is itself an illusion at the quantum scale. And a small but serious group of physicists goes further. They say entanglement is evidence that space itself, the distance between objects, might not be fundamental, that space emerges from something deeper, something we haven't named yet. This is where the science stops being settled and starts being a genuine investigation. Here's what makes entanglement so philosophically destabilizing. It's not just a laboratory curiosity. It's already being used. Quantum cryptography uses entanglement to create theoretically unbreakable encryption. The moment a message is intercepted, the entangled state collapses, and the eavesdropping is instantly detected. China has already launched a quantum satellite network. The European Union is funding a quantum internet. The United States has a national quantum initiative. Entanglement is real enough to build technology with, real enough to spend billions on. And yet, the how remains unanswered. The 3 leading interpretations of quantum mechanics each give a radically different explanation. And physicists genuinely disagree about which, if any, is correct. The Copenhagen interpretation says, don't ask. Measurement produces results. The mechanism is beyond the question. Accept the mathematics. Stop asking about reality underneath. The many worlds interpretation says, every measurement creates a branching. When you measure a particle, both outcomes happen. In parallel universes that immediately separate, there is no instant connection because all outcomes already exist. And the pilot wave theory, championed by physicist David Bohm, says Einstein was almost right. There are hidden variables, but they're non-local. A hidden field guides particles across any distance, instantly, in a way that preserves all of quantum mechanics predictions while keeping reality deterministic. 3 theories, all mathematically consistent. No experiment, yet capable of distinguishing between them. This is the state of physics at its deepest level. Not confusion, but genuine, productive mystery. The kind of mystery that has driven every major scientific revolution in history. And here is what strikes me most about quantum entanglement. If two particles can be permanently connected, if measurement here can instantaneously affect something there across billions of light years, then what does separation even mean? At the scale of particles, the universe doesn't seem to respect the distances we observe, the boundaries we experience between here and there, between me and everything else, may not exist at the most fundamental level. The universe, it turns out, might be far more connected than it appears. So I'll leave you with this. We started with two particles, separated by any distance, instantly connected. We followed the evidence. Through Einstein's objection, through Bell's theorem, through Nobel Prize-winning experiments. The connection is confirmed. The mechanism is unknown. But the deeper question isn't about particles. If the most fundamental objects in the universe can be non-locally connected, if separation itself might be a kind of illusion at the quantum scale, then what does that say about us? We are made of particles, billions upon billions of them, particles that have been interacting and entangling since the beginning of the universe. Maybe the boundary between you and everything else is less solid than it feels. Maybe, at the deepest level of reality, nothing is truly separate. What do you think? Is quantum entanglement just a physics phenomenon? Or does it say something deeper about the nature of existence? Leave your answer below. I read every single comment. And if this investigation opened a door you want to keep exploring, subscribe. Because next week, we go deeper.